There are a lot of hydrocarbons with carbon, hydrogen, and oxygen in them. And an example of this is drinking alcohol, ethanol, which has carbon, hydrogen, and oxygen. If you've ever used acetone to remove like nail polish from nails and stuff, that's a carbon, hydrogen, oxygen compound. And if you have oxygen, there's one little twist we have to do. So in this example, it's going to start out similar to what we did, but there's going to be a small twist. And also in this example, we're going to go not just to the empirical formula, but we're going to go to the molecular formula. Now, this example uses something called caproic acid, and supposedly it has the smell of dirty gym socks. I am fortunate to never have had the opportunity to smell it. I will take people's word for it. But caproic acid, like a lot of acids, has carbon, hydrogen, and oxygen in it. And what we're doing in this problem is you're taking 0.450 grams of caproic acid and you're burning it in O2, and the products, once again, water and CO2. All right. And so that part is kind of like what we did before. However, they're also throwing in here the molar mass of this compound, the whole thing, 116.2 grams per mole. Notice this grams, moles, -1. Moles -1 can also be written as 1 over moles. For example, x to the -1 is 1 over x. So moles -1 is like 1 over moles. So if you see this grams, moles, -1, and you will sometimes, that just means grams per mole. All right, just an alternative way to write molar mass. What is the molecular formula of caproic acid? Now again, caproic acid has carbon, hydrogen, and oxygen in it. So this problem will start off similar to what we did, but it's going to go a little bit different. This compound is different because it is a hydrocarbon with carbon and hydrogen, but it also has oxygen. And this reacts with more oxygen, more O2, to make CO2 and water. So the question is, which oxygen comes just from the acid and what oxygen comes from the O2? And of the CO2 and water oxygen, which of those came from just the caproic acid? So it's the oxygen here which is tricky, but we're going to use law of mass action to figure out how this works. We did not use the grams of the sample in the first example with the carbon and hydrogen thing we looked at, the C3H4 example, but we are going to use this 0.450 gram sample in this problem. Starting it off, we're going to start the same way we did in the last one. We're going to go grams of water and carbon dioxide to moles of water and carbon dioxide, then turn them into moles of hydrogen and moles of carbon, just like we did last time. So here's the example. We'll start with water, 4.418 grams of water. Here's the molar mass of water, turning grams water into moles. 2 hydrogens for every 1 water. This number here, 0.0464, represents the moles of hydrogen, and that's just like what we did earlier. However, this next step is kind of different. I'm going to take that number, the moles of hydrogen, and multiply it by the molar mass of just hydrogen. And to 3 sig figs, that's 1.01 grams. So 0.0464 moles of hydrogen represents 0.0469 grams of hydrogen. And I put both of those numbers in red because we're going to use both of them again here in a little bit. Hint, hint. Now we're going to do the same process, but now with the CO2. We'll start with the 1.023 grams of CO2. We'll turn it into moles using the molar mass. 1C from 1 CO2, so 0.02324 is the moles of carbon. And again, it's in red. And that's, again, that part is similar to what we did earlier. Earlier, we would have then compared moles of C and moles of H to find a formula, and we would have been done. But the oxygen is there. So, continuing on, I'm going to take that same moles of carbon and turn it into just grams of carbon. So 0.02324 moles of carbon represents 0.2791 grams of carbon. Why did we do that, Dr. Russell? Oh, I'm so glad whoever asked that question. The point, let me get the exact number. There it is. The 0.450 grams caproic acid represents all of the carbon, hydrogen, and oxygen oxygen in the sample. And notice that's a gram number. And notice 0.450 grams is less than 0.0469 plus 0.2791. And that's good. The difference is going to be the grams of oxygen in the sample. So again, the sample, 0.450 grams, that's all the carbon, hydrogen, and oxygen in this caproic acid. And we're going to subtract the grams of hydrogen and the grams of carbon to get just the grams of oxygen in the caproic acid. Oh, I get excited by these problems. Oh, nerdy chemist. All right, sorry. Keep on target. Keep on target. Anyway. So 0.450 grams caproic acid is all of the C, H, and O, and specifically all the grams carbon, hydrogen, and oxygen in the complex, in the caproic acid. So if we know that caproic acid has 0.0469 grams of hydrogen and 0.2791 grams of carbon, which we got, by the way, from the CO2 and water converted over, then the difference is going to be grams of oxygen. So you can see what we did here, 0.450 grams, the grams of everything, minus grams of hydrogen, minus grams of carbon, 0.124 grams of oxygen. And that, my friends, is the grams of oxygen in the caproic acid. It has nothing to do with the O2 that was used to burn the sample. And that's the only way that I know of, well, unless you want to get in complicated mass percentages, which I don't recommend, that's the best way to do to figure out the grams of oxygen in this crazy thing. All right, it's the difference of masses. And you can turn the 0.124 grams of oxygen into moles. Mole of oxygen about 16 grams, 0.00775 moles of oxygen. So now we've got moles of oxygen here. We had moles of hydrogen and moles of carbon on the previous slide. If we put this all together, we have a rough formula that looks like that, but it's pretty ugly. So like we did at the end in the last section, we're going to divide all three of those numbers by the smallest number, by 0.00775. That comes out to be 3 carbons, 6 hydrogens, 1 oxygen. So C3H6O, that's the empirical formula of the caproic acid. And again, getting the oxygen was the funky part. We had to subtract the C and H away from the total 0.450 grams to turn in the moles. But that's how this is done. Now, empirical formula, not the final answer. We need to figure out how the empirical formula relates to the molecular formula, and that's where we need the molar mass, which we haven't used yet. So in this problem, if you add up 3 carbons and 6 hydrogens and 1 oxygen, or roughly 3 times 12 plus 6 times 1 plus 16, it comes out to be about 58.1 grams per mole. And you can compare the empirical formula's molar mass, which is this number, to the molar mass of the whole thing, which is the number that's given to you. And you can probably see that 116.2 divided by 58.1, that's a ratio of about 2 to 1. So that means the molecular formula will have 2 empirical formulas in it. C6H12O2 is the molecular formula. So this is a pretty cool thing. You can find formulas based on elemental percentages, and that's what we did at the end of the chapter 2, part 2 stuff. We took like percents of compounds to find empirical formulas and molecular formulas. This is an alternative way. This is based on what's called combustion analysis. Combustion means to burn, and we're burning these crazy things in oxygen to make CO2 and water. You can use those pieces of information then to find a formula too, and that's a pretty powerful technique. Both of these are used in chemistry. It just depends on where you are and what you're doing at the time to know which one is the best answer for you.